Look up at the night sky. What do you see? Stars, planets, galaxies, maybe, if you're lucky, a shooting star or two. For thousands of years, we humans believed that what we see is what we get, that the universe was made of this. Everything you've ever seen, every star in every galaxy, in every corner of the observable universe, all the planets, all the gas clouds, all the dust, every atom that makes up your body, your phone, your dog, your breakfast, all of it. Every single thing we can detect with every instrument we've ever built.
Thank you, Liam, for that very interesting story. Now, I will take the narrative part. As you know, 95% of the universe is invisible, and we have no idea what most of it is. Today on our channel, we're going to try to answer one of the biggest questions in modern science, but I'm going to warn you right now,
we still don't fully know.
and that's actually the most exciting part, because the answer might change everything we think we know about reality itself. Our story begins not with what we couldn't see, but with what we couldn't explain. It's the 1930s. A Swiss-American astronomer named Fritz Zwicky is looking at the Coma Cluster, a massive collection of over 1,000 galaxies all hanging out together in space. And he notices something that makes absolutely no sense. These galaxies are moving way too fast. According to everything we knew about gravity at the time, they should have flown apart long ago. They should be scattered across the cosmos like marbles on a tile floor, but they're not. They're stuck together. Something is holding them in place, something with a tremendous amount of mass. But when Zwicky looks for that something, he can't see it. He calls it dunkle materie, dark matter. Fast forward to the 1970s, astronomer Vera Rubin is studying individual galaxies. She's looking at how stars rotate around galactic centers. And here's what you'd expect to see based on how planets orbit our sun. Planets that are farther from the sun move slower. That's just basic Newtonian physics. It should work the same way in galaxies. Stars near the edge should be crawling compared to stars near the center. But that's not what Rubin found. Not even close. The stars at the outskirts of galaxies were moving just as fast, sometimes faster, than the stars near the center. It was as if an invisible hand was pulling on them, keeping them from flying away. As Rubin herself put it, even stars at the periphery are orbiting at high velocities. There has to be a lot of mass to make the stars orbit so rapidly, but we can't see it. We call this invisible mass dark matter. And here's the mind-bending part. For this to work, each galaxy has to be surrounded by a massive halo of invisible matter, a cosmic cocoon of dark stuff that reaches far beyond the visible edge of the galaxy. We're talking about dark matter outweighing visible matter in some galaxies by a ratio of 9-to-1, but it gets even bigger because dark matter didn't just hold galaxies together. It built the entire structure of the universe. In the early universe, right after the Big Bang, dark matter started clumping together under its own gravity. These clumps then pulled in ordinary matter, the stuff we're made of, creating regions dense enough for the first stars and galaxies to form. The result is what astronomers call the cosmic web, a vast, almost invisible network of dark matter filaments stretching across the universe, with galaxies hanging on them like beads on a string. Without dark matter, there would be no galaxies, no stars, no planets, no you, no me. And here's the real kicker. We have photographic proof that dark matter exists. Well, sort of. It's called gravitational lensing. Einstein showed that massive objects bend the fabric of space itself. Light bends around them. When we look at distant galaxies, we can see their light being warped and magnified by something sitting in front of them, something massive. But when we look at that something, there's nothing there, just empty space. The only conclusion is that invisible mass is bending that light. And when astronomers map these distortions, the dark matter map matches exactly where we'd expect it to be based on how galaxies are moving. So we know dark matter is real. It shaped the universe. It holds galaxies together. But the million-dollar question, actually the billions of dollars in research question, is what is it made of? So what could dark matter possibly be? Here's where things get really interesting. At first, scientists thought maybe it was just regular stuff we couldn't see, faint stars, black holes, cold gas clouds. They called these MACHOs, massive, compact halo objects. Makes sense, right? Maybe it's just really hard to see, but telescopes got better, and we realized there just aren't enough MACHOs to account for all the missing mass. It's not even close. So physicists turned to the world of particle physics, and they proposed something much more exotic, entirely new types of particles that almost never interact with normal matter. The leading candidates are called WIMPs, weakly interacting massive particles. These things are heavy, they move slowly, and they can pass through you, me, the Earth, the sun, like we're not even there. Then there are Axions, ultralight particles that would be everywhere, like a ghostly fog permeating the entire universe. Some scientists think dark matter might be a combination of different particles, or maybe something even stranger that physics hasn't even imagined yet. To find these particles, scientists have built some of the most sensitive instruments on Earth. Take the LZ experiment, buried deep underground to shield it from cosmic rays. It's a massive tank of liquid xenon, waiting for the incredibly rare moment when a dark matter particle might bump into a xenon atom. The LZ experiment just released its latest results using the largest dataset any dark matter detector has ever assembled. And the result? Nothing, no dark matter detected. But here's the thing. In science, a null result isn't a failure. Every time we rule out another possibility, we get closer to the truth. We have now eliminated certain mass ranges for WIMPs. We know more than we did before. Meanwhile, telescopes like the James Webb are mapping the cosmic web in unprecedented detail, showing exactly how dark matter and ordinary matter grew up together in the early universe. But dark matter is only half the story. Actually, it's less than half, because there's something even stranger out there. Something that's been hiding in plain sight the whole time. While astronomers were trying to figure out dark matter, they accidentally stumbled upon something even more baffling. Most of the 20th century, scientists assumed that the universe was expanding, but that it was slowing down. The Big Bang happened, everything flew apart, and gravity was supposed to gradually pull everything back together. It just made sense. Like throwing a ball in the air, it slows down, stops, and falls back. So in the late 1990s, two teams of astronomers set out to measure exactly how much the expansion was slowing. They looked at distant supernova, colossal exploding stars that act as standard candles for measuring cosmic distances. These supernovae all explode with roughly the same brightness. If you know how bright they should be, and you measure how dim they look from Earth, you can figure out how far away they are. Simple, right? But the results didn't just surprise them. They shocked the scientific community to its core. The distant supernovae were dimmer than expected, much dimmer, which meant they were farther away than they should be. And there was only one explanation. The universe wasn't slowing down, it was speeding up. The expansion of the universe is accelerating. Astronomer Brian Schmidt, who led one of the teams, said, "My own reaction is somewhere between amazement and horror. Amazement because I just did not expect this result, and horror in knowing that it will likely be disbelieved by a majority of astronomers." They called this mysterious force driving the acceleration dark energy. And here's where it gets really wild. Dark matter and dark energy are basically opposites. Dark matter is attractive. It pulls things together through gravity. It's the cosmic glue holding everything in place. Dark energy is repulsive. It's like anti-gravity. It pushes things apart, working against gravity on the largest scales. While dark matter built the structures of the universe, dark energy is slowly pulling those structures apart. And here's the part that really messes with your head. Ordinary matter, everything we've ever seen, is about 5%. Dark matter is about 27%. And dark energy is 68%. Nearly 70% of the universe is this mysterious force that we only discovered 25 years ago. Now, here's the irony. Einstein actually predicted something like this back in 1917. He added what he called a cosmological constant to his equations of general relativity to keep the universe from collapsing under its own gravity. He called it his biggest blunder and abandoned it. Turns out he might have been right all along. The cosmological constant could be exactly what dark energy is, a fixed amount of energy woven into the very fabric of empty space itself. Think about that. Every cubic meter of what looks like empty space has a small, constant amount of energy in it. As the universe expands, more space is created, which means more dark energy appears. It's not that dark energy is spreading out, it's that there's more of it as the universe gets bigger. Other theories suggest dark energy might be a dynamic field that changes over time, called quintessence, or something even more exotic called phantom energy that could get stronger and eventually tear the universe apart. So, what does all this mean for the future of the universe? Well, that depends on what dark energy really is. If dark energy is the cosmological constant, a fixed, unchanging force, then the universe will keep expanding forever, faster and faster. Galaxies will drift farther apart, the night sky will grow empty, stars will burn out. Over trillions of years, the universe will approach what scientists call heat death, a state of eternal darkness and cold, the big freeze. But if dark energy behaves like phantom energy, where the repulsive force grows stronger over time, we're looking at a big rip. Space expands so violently that galaxies are torn apart, then solar systems, then planets, then atoms themselves. It's the cosmic equivalent of getting stretched until you're nothing but scattered particles. If that happens, here's the timeline. About 60 million years before the end, our galaxy gets torn apart. 3 months before the end, the solar system unbinds. 30 minutes before the end, the Earth explodes. And fractions of a second before the end, the atoms that make up everything in existence are ripped apart at the subatomic level. Now, before you panic, current observations slightly favor the cosmological constant over phantom energy, but the measurements aren't precise enough to rule it out. We still don't know. That's why missions like the European Space Agency's Euclid telescope are so important. Launched in 2023, Euclid is building a 3D map of the universe, observing billions of galaxies out to 10 billion light years. It's designed to answer two simple questions. What is the nature of dark matter? And what is the nature of dark energy?
Albert Einstein once said, "The most beautiful experience we can have is the mysterious. It is the source of all true art and science." We live in a universe where 95% of what exists is invisible to us. We are creatures made of stardust, drifting through an ocean of dark matter and dark energy that we're only beginning to understand. We don't have all the answers yet. Maybe we never will. But that's what makes this so incredible. Every experiment, every observation, every failed detection brings us closer to understanding the true nature of reality. The story of dark matter and dark energy is still being written. It's a story of humility and boldness, of questions that reach beyond science into philosophy. In the darkness that surrounds us lies the promise of discovery, the thrill of pursuit, and the enduring truth that the universe, no matter how mysterious, is comprehensible to the human spirit that dares to seek. This is VovaKnowItAll, reminding you that the universe is stranger than we can imagine, and that's exactly why we should never stop asking questions. Don't forget to like, subscribe, and hit that notification bell, because the next mystery might be even crazier. And hey, if you've got a crazy question you want me to tackle, drop it in the comments. Because around here, we know, or at least we're trying to find out.